Swayam Prabha. Digital India. Educated India.
Alright, so we just did an example where we had solved a problem of a bolt group where a number of bolts were subjected to a force which was introducing a torsional effect on the bolts. Since the bolts individually cannot resist any torsion, the lever arm between the bolts was able to resist that torsion, that twisting moment, and we solved that problem, and we found out how to calculate the forces in the individual bolts for a given twisting moment. Now, a similar kind of a problem can be also addressed by using welds. So, similar kind of structure is shown here. Here you have a column and a bracket. The bracket is supported by the column, and the bracket is resisting a load which is acting at this location P at an angle 60 degree again from the horizontal. And this time the bracket is welded to the column rather than bolted. And this weld this time is not a symmetric weld. Even if it were symmetric, still there are issues associated with the situation of with the configuration of this bolt that we will take a look at. Okay, so just a few more details that I would want to emphasize. The problem is that we need to the problem statement is that we need to calculate the maximum value of P that a 6 millimeter weld as shown in this figure can resist. Okay, so we need to find out what is the maximum P value that this weld can resist safely. The steel that is used is Fe410, so its ultimate stress is 410 MPa. The weld dimensions are mentioned. The horizontal portion of this weld is 170 millimeter. This is a fillet weld, and the vertical component of this weld is 300 millimeters. So one vertical leg and two horizontal legs. All right, and the plate thickness is given as 10 millimeters. We need not check all that because 6 millimeter weld is provided, that is already given to us. The load, the point where the load is acting is 300 millimeters away from this edge of the weld. Okay, and also the weld length is 300 millimeters, and that is exactly the same height where the load is acting. Okay. All right. So in this thing, let me just mention that we will call 300 as D, small d, and 170 as small b. Okay. So this is a rather interesting configuration if you see, but this is a very common one. What would happen is that because of the load, the way it is acting, it will introduce a direct stress like it did for the bolt group. So because of this force that is acting here, every portion of the weld will be subjected to this kind of a force demand, isn't it? So there will be a force that will be acting because of this, and assuming that the plate that assuming that this bracket plate is very stiff, we can make a deduction that if the plate is stiff, the different portions of this weld will be deforming by the same amount. And also another assumption that we can make is that all these small portions of these welds, if you can imagine small segments, all those portions are having equal stiffness, right, when they are subjected to this force. So if every weld portion has equal stiffness, irrespective of its orientation, so this weld is in this orientation, this weld is in this orientation, but when subjected to this load, we are making an assumption that they all have the same stiffness. We will get into that point where this assumption is not really true. But for the time being, we are making that assumption, and with that assumption, we can calculate what is the direct effect of this force. However, that would have been the resistance, or that would have been the stress had this force been acting actually at the centroid of this weld group. But this force is not actually acting here, but it is acting at an eccentricity which is this much here. So this eccentricity we need to calculate. How much is this eccentricity? The eccentricity in this direction, in the x direction, which is relevant for the force, the vertical component of the force, we will call it Ey. This is equal to 300 millimeters here, and the distance of the centroid from this edge. that is added together. So that is your eccentricity that is relevant for the y component of the force. So we will call it Ey, even though it is in the x direction. Likewise, the eccentricity which is to be multiplied with the horizontal force will be this distance. Okay, and we will call it Ex. So we will be using these two quantities later on. Now what happens is that because of this force, the way it is acting, it introduces this moment, right? So other than this direct force effect, it also has a moment effect. This moment is basically making this weld twist this way. So this is kind of a twisting action. And again, like in the previous case, individual portion of the weld, let's say there is a small portion of the weld here, and its radial distance is marked here in this line. So there is a force demand on this weld which is perpendicular to this radial line. Okay, and this force direction keeps changing for every weld segment, isn't it? So let's say we take a segment here, its radial line is in this direction. So the force because of the twisting moment will be in this direction, and so on. So they will be all resisting the force, the twisting in these respective directions by applying a force in these directions, and we need to account for all of that. Now, this is obviously a twisting situation, so we know that the inertia against twisting is basically known as polar moment of inertia, IP, which is equal to Ix plus Iy, wherein Ix and Iy would be, if we calculate the moment of inertia about this horizontal axis, we can call it Ix, and if you calculate the moment of inertia about the vertical axis, so we need to calculate the neutral axes in x direction and y direction. And when we calculate the moment of inertia about these two axes, we add them together and we get IP, polar moment of inertia. So that is one quantity that we will have to utilize. So basically the idea is that first we would calculate the direct stress. F prime x and F prime y basically represent the direct stresses, which are all parallel to each other because they are parallel to the direction of the force. In addition to that, there is another component of Fx and Fy which arises out of the effect of the twisting. So the stress in any component, if we take a small component, the stress because of twisting in this component will be equal to the twisting moment T multiplied by the distance, the radial distance. So here when I say y, I mean the vertical component of the radial distance, T multiplied by y divided by the IP value. Similarly, this is the x component of that force. The y component of the force will be T multiplied by x divided by IP, which is written here. So this is the vertical component of the force which is resisting the twisting moment. Okay, and if we can calculate the total twisting action, we can calculate these values as well. Okay. So that is the basic philosophy that we will follow, and again, like in the previous case, the entire weld will not be subjected to same amount of force. So different portions of the weld will be at different level of stress, and we need to identify the area which is under the highest stress and then design for that. The rest of it can be automatically considered to be safe. The calculation of IP may not be always very straightforward. Sometimes, depending on the geometry, it can be slightly complex. We have to calculate Ix and Iy. So we can calculate it ourselves, but also there are some guides available to us. So there is this table which was developed by this author in 1966. I have taken this table from the textbook, that is Dr. N. Subramanian's book. For different commonly used weld shapes, weld geometries, it provides you the location of the neutral axis, if it is not obvious, if it is not symmetric, and also the polar moment of inertia and section modulus as well. So we can utilize these to calculate some of these critical properties. So the section, the shape that we are talking about resembles this one, number 5 here, right? So this is how our weld shape was. So B was the width of the base, the bottom weld, which was 170 millimeter, and D was the depth of the weld. The neutral axis distance, x bar, for the vertical neutral axis is given as B square divided by 2B plus D. And the polar moment of inertia IP for this entire weld is given by this expression, which is basically again a function of B and D values, which we understand what it is, right? So we will use this expression. So we will go step by step to calculate the strength of this weld and calculate how much is the maximum force this weld can resist. By the way, the method that we have just discussed is known as elastic vector method, and we will get to the assumptions here and what are the drawbacks of this approach. So one assumption here is that we are assuming that material is elastic throughout. Other assumption is that the stiffness and strength, when I say material, I mean weld material, and strength do not depend on the orientation. So therefore, the idea of IP, which was developed for isotropic material can be applied. The moment of inertia concept can be applied directly only with these assumptions. If we assume that stiffness and strength do not depend on the orientation. What do I mean? As we had seen in the beginning, for fillet welds, if the force is applied in this direction, we call it an edge fillet. But if the force is applied on a fillet in this direction, then it is called an end fillet. And the strength and stiffness values are very different between the two. However, in this particular case, we are assuming that all these welds perform exactly the same. And that with that assumption, we can do this kind of an analysis. Okay. So first thing that we will do is that we will calculate the value of x bar, which is given by b square divided by 2b plus d. We know that b is equal to 170 and d is equal to 300. Now we substitute these values, and what we get is this value turns out to be 45.15 millimeters. And also we can calculate the IP value. For us to be able to calculate the IP value, we will substitute the respective values in this expression. So once we substitute these values, we get IP as 11.87 into 10 to the power 6 millimeter cube. Okay. So this is the polar moment of inertia and this is the location of the neutral axis. Now, like before, first we need to calculate the moment demand. Okay. So moment demand, earlier what we had done was we had taken the force and we had tried to calculate the distance of the eccentricity with respect to that total force. This time we will do it slightly differently. Either approach is fine, but this time let's try it slightly differently just to showcase that there are two ways to do it. We will take a px component and then we will take a py component. And then we will calculate the eccentricity for px separately and we will calculate the eccentricity for py separately. That might make some calculations relatively cleaner, even though it may take slightly more time. So the px component can be calculated as p multiplied by sine 30 and py component can be calculated as p multiplied by cos 30. Both of them will be equal to, the first one will be 0.5p and this one will be equal to 0.866p. So we have calculated the two components. Now we can calculate the eccentricity in each direction. So eccentricity Ex. Now Ex is the eccentricity which needs to be multiplied with Px. So this is the eccentricity Ex, even though it is in y direction. So Ex is equal to 150 millimeters from the centroid of the weld to the load. And Ey will be the eccentricity from here to the point of loading. This is Ey. How much is that? This is basically equal to this distance 300 millimeters plus this distance. And how much is it? This distance is basically equal to 170 minus x bar. So we will call it 300 plus 170 minus x bar, which turns out to be, and we had calculated the x bar value, right? X bar was calculated as 45.15. So we substitute that here and what we get is 424.85 millimeters as the Ey value. Okay. Now, all this calculation is being done to calculate the moment demand. The twisting moment now can be calculated as Px Ex plus Py Ey. Right? So Px is known as 0.5 P, and P we don't know yet, so we will keep the P term as unknown. 0.5 P multiplied by 150. Also be mindful that this will have a direction in moment in this direction, which will have an anti-clockwise effect, and Py will have a clockwise effect. So anti-clockwise and clockwise, let's calculate T in clockwise direction. Therefore, we will put minus 0.5 P multiplied by 150 plus 0.866 P multiplied by 424.85, which will be equal to 292.92 P. These many, if P is in newtons, these many Newton millimeters. Okay. So that is the twisting moment demand. Okay. Now we can take the next step and calculate the actual stresses or actual forces in each segment. So force demand over a unit length. So first we can calculate the Fx because of the applied force directly and Fy because of the applied force directly. Then we can calculate Fx because of the twisting moment and Fy because of the twisting moment. So Fx because of the applied force directly will be very simple. We will have Fx, which is total force is 0.5 P, isn't it? That is 0.5 P is marked here. So that is the total force in x direction divided by the length of the weld. What is the length of the weld? LW is equal to 300, that is the vertical leg, plus 170 multiplied by 2, which turns out to be 640 millimeters. So we will divide by 640 here, and which turns out to be 0.7813 multiplied by 10 to the power minus 3 P. Likewise, Fyp will be equal to 0.866 P, which was the total force, divided by 640, and that is 1.3531 into 10 to the power minus 3P. If you want to calculate the moment, the force per unit length because of the twisting moment, the approach we would have to use is first twisting moment multiplied by, if we are calculating Fx, then we have to take the distance y divided by Ip. Now, these two forces, Fx because of P and Fy because of P, they were uniform throughout the length of the weld, because we had made this assumption wherein we had said that the stiffness and orientation do not matter. So stiffness remains uniform throughout, irrespective of the orientation of the weld. So distance and orientation did not matter because the P force was acting at the centroid. But actually the P force is not acting at the centroid, and there is a moment effect of that. Now that moment, of course, the force will change. The force because of that moment will change, because each weld is, or each segment of the weld is at a different distance from the centroid. Just to emphasize, as we had mentioned, if this portion of the weld is at this distance from the centroid, it will contribute more towards resisting the moment, and the contribution, its contribution towards resisting the twisting moment will be proportional to this distance squared, right? The reason for that is, first, the force for a given rotation, the force in that segment will be proportional to the distance, right? And in addition to that, the moment because of that force will again be proportional to the distance. So because of that, there is this distance has a two factor, comes twice in the equation. So now we do not know, for each segment the force value will be different, that is the force that it applies to resist the moment, that will be different. So for which segment should we look at? So again, we know that corners will be the ones that are going to be critical from this point of view, because corners are the farthest apart locations, right? So we should actually be looking at the four corners, and one of those corners will be giving us the highest value. Now between the four corners, let me call it corner 1, 2, 3 and 4, between these among these four corners, corner 4 and corner 1 are the farthest. So they should be giving the highest force demand because of the moment. Corner 1 and corner 2 and 3 will give you a slightly smaller force demand because of the moment. In addition to that, also the resistance or the force because of the moment, because of the twisting at corner 4 is almost aligned with the force that is acting at corner 4 because of force P directly, right? So again, the same principle will apply that we applied in the previous example. These two forces are almost parallel to each other, and therefore the net contribution of these forces at corner 4 will be the highest. So let's look at only corner 4. Again, Fxt and Fyt need to be calculated only at corner 4. This would change if the orientation of the force changes. If the force is acting in some other direction, this location would change. But for this orientation, the way this force was applied, it should be corner 4, that should be the critical one. Okay. So, why we have to use y? Because we are talking about force in x direction. So, the moment will be, you have to multiply it with y. We substitute the values. 292 point, the torque value was, or the twisting moment value was 292.92 p multiplied by y is 150 for that corner 4, right? So this corner is at a distance of 150 millimeter in y direction and at a distance of 170 minus x bar is equal to 124.85. Okay, that is the distance from the centroid. So we substitute 150 for y divided by IP. IP we had already calculated, which was equal to 11.87 into 10 to the power 6. And this turns out to be 3.702 multiplied by 10 to the power minus 3p. Similarly, Fyt can also be calculated. This is again equal to t multiplied by x divided by ip, and that will be equal to 292.92 multiplied by p multiplied by 124.85 divided by 11.87 into 10 to the power 6. And this, in y direction, the force is 3.08 into 10 to the power minus 3p. Okay. So now we have calculated fx and fy values in fx and fy values because of the force p directly and because of the twisting moment. Now total fx can be calculated, total force can be calculated. Force per unit length is equal to square root of fxp plus fxt squared plus fyp plus fyt squared. Okay. So when we substitute the values, what we get is 6.306 multiplied by 10 to the power minus 3p. We have basically substituted these fx and fy values here. This is what we get. This is total f internal. And now what we need to do is, this is the demand for a given p. We need to calculate the capacity of the weld. So it is given that it is a 6 millimeter fillet weld, right? So the capacity for this weld would be, if the weld size is 6 millimeter, its throat thickness would be 6 multiplied by or 6 divided by root 2. Then as per the Indian code, the strength is governed by Fu divided by root 3. This is the material property that we would use, material strength, that is Fu divided by root 3. Fu is the ultimate stress of the parent material, and root 3 is the factor for von Misses stress. divided by 1.25. This is the gamma value to represents the shop welding of this thing. Okay, so now and multiplied by the LW, but LW is given as LW, we are assuming unit for the time being, and this can be calculated as 795 Newton per millimeter. So this is the capacity of this weld per millimeter length, and the demand was this much. So from this, when we equate the two, we can get P is equal to 795 into 10 to the power minus 3, if we write this in kilonewtons, divided by 6.306 into 10 to the power minus 3, and this turns out to be 126 kilonewtons. Okay. So basically what it means is that we can apply 126 kilonewton external load at that orientation to resist the to resist this load safely. Okay. Now that is the capacity for a single plate. It is also mentioned in this one, bracket on either side of the column. That means there are two such plates. So if there are two plates, so we will use 2P. So therefore 2P will be equal to 126 multiplied by 2, which is basically equal to 252 kilonewton. All right.